We are going to be talking more about complex numbers in their trig form, and we're going to be doing powers and roots of complex numbers in day 2 of section 6.5. Powers and roots of complex numbers. So think back to yesterday, we were able to change forms, rectangular form to trig form and vice versa. We also looked at some formulas in trig form for multiplying and dividing the trig or the complex numbers in trig form. And I didn't get to prove that with you, but of course you can look that up in the textbook or you can try it. Ask me about it tomorrow. We can look at that. It's pretty easy proof other than you have to multiply and distribute things. But today we're going to look at some other operations, which would be taking powers of complex numbers and taking roots of complex numbers. So I'm going to start off with where we do some powers, sort of like the long way, using our multiplication rule from yesterday. And I'm going to see if you guys can see the pattern, if you could write the rule that I'll give you on the slide after our first slide. Okay, so I'm going to start with doing some powers of complex numbers. So I'm going to choose a complex number z. Remember, z is commonly used for the complex number set. And I'm going to call my complex number r times the quantity cosine theta plus I sine theta, which you could also just write as r cos theta. So if you prefer the shortened abbreviated form, I know, because I like to write as little as possible. So I'm going to use that r cos theta there. Now, this is going to show for any modulus r, for any argument theta. So I'm not going to plug in actual numbers. I'm going to leave them as r's and thetas. Now, the next thing that I want to do is I want to raise it to a power. So I want to do z squared. Let me ask you this question, just basic mathematics. What does it mean to square a number? Multiply it by itself, Emily says. So we're going to take z, r cos theta, and we're going to multiply it by itself. So we're going to take r cos theta times r cos theta. And we have a multiplication rule from yesterday. So we have a multiplication and division rule from yesterday. In multiplication, it would tell you if you're multiplying two complex numbers in trig form, then you're going to take the modulus from each complex number and multiply them. So our modulus for each of these is r. We're going to take r times r to get r squared. Then, in that multiplication rule, you do the cos theta times cos theta, and we were told that when we multiply those things together, and this is the work that I didn't show you that you could look up in your textbook, it will simplify every time to be cos of the two arguments added together, so the sum of the arguments. So what's theta plus theta? 2 theta. That looks pretty good. So if I multiply r cos theta times r cos theta, I'm going to get r squared cos 2 theta. Now, I'm going to do another power. So now I'm going to take z, r cos theta, multiply by itself 3 times. R cos theta times r cos theta times r cos theta. Well, the nice thing is I've already done r cos theta times r cos theta. So I know z squared is r squared cos theta, r squared cos 2 theta. And I'm going to multiply it by another z, which is r cos theta. So that would tell me multiply the modulus of each, r squared and r, to get r cubed. Thank you, Ethan. And then when I multiply cos 2 theta times cos theta, that will turn into the cos of the sum of the arguments. So cos of 2 theta plus theta is 3 theta. Oh. Are you starting to see a pattern? David.
If you were to split that up into sine and cosine instead of integers, how would that work?
It would look like the cosine of 2 theta plus I times the sine of 2 theta in parentheses times the cosine of theta plus I times the sine of theta in parentheses. You'd have two binomials and you'd have to like FOIL or distribute that out. And that's the part where, like I just gave you the formulas yesterday, it will always simplify to be the cosine of theta sub 1 plus theta sub 2 plus I times the sine of theta sub 1 plus theta sub 2. And that's in the textbook, and I could show you that tomorrow if you want to see it. Okay, so you would actually have to like multiply the binomials. Okay, we just accept the formula to be true. I'd like for you to think really quickly in your head what you think z to the 4th is going to look like, and you could jot that down what you think it's going to be. So I've only done really 2 powers. I'm going to go ahead and do this one the long way again and just verify that it is what I think it will be. And I have 2 ways to do z to the 4th. I could take z squared times z squared, or I could do z cubed times z. Both of those would be z to the 4th. I'll just go with my z cubed. So r cubed kiss 3 theta, and then multiply it by another z, which is r kiss theta. And follow the same work that I've done previously. R cubed times r is r to the 4th. Kiss 3 theta times kiss theta is now kiss 4 theta. Is that what you thought it was going to be? Cool. So could you please write the rule for z sub n? Or sorry, z to the n. What would the rule be for z to the n? Share really quickly with your table groups. What did you write? What does it look like? Should look something like this. R to the n, kiss, n theta. Okay. Important to note, n and theta must be multiplied before you were to do like cosine or sine. Okay, so if you wanted to, you could add a group of parentheses there. But I think most of us understand that we have to multiply that first. And we're not just doing kiss of n and then multiplying by theta. Okay, good. Okay, so that is a theorem called de Moivre's theorem. And I would like for you to make sure you at least write down the name de Moivre in your notebook, because some of the directions in the textbook or in your review or on your test might say use de Moivre's theorem. So that would be helpful if you knew which one that was. And this one is written out like fully, cosine n theta plus I times sine n theta. You could also write that out as you did in your table groups, which is kiss n theta. Okay, so if you prefer that. And I put a little note there as well. Theta should be between 0 and 360. In the very beginning, okay, before you do any work. Okay, so let's put this to work, de Moivre's theorem. We can use de Moivre's theorem then to expand and do the power of -1 plus I to the 6th. Now, I do really quickly just want to take you down a little road of all your other previous math classes, all the knowledge that's really inside your head somewhere. You can do this without the work that we've done. Okay. One way I call the long way, and the long way would be to write out that binomial, -1 plus I, 6 times. -1 plus I, -1 plus I, -1 plus I, and then do the multiplication. Multiply 2 at a time, then multiply again, then multiply. Remember the roller coaster project that you did in semester 1? And you pick all those roots for your roller coaster and you multiply them all out. Remember how much work that became at the end? Okay. That's what that would turn into, because you got to do it 6 times. Okay. The other option that you have, though, is since this is a binomial raised to a power, you have two sort of methods that can work together. The binomial theorem is a way for you to expand powers of binomials. It starts off with like a combination of n choose 0 times a to the n and b to the 0. Where you take the first term, raise it to the highest exponent, the second term, raise it to the lowest exponent, and you do that combination. The other way to work that is instead of using the combination, you would use Pascal's triangle to figure out that coefficient. Okay, so you would go down to the row in Pascal's triangle that starts off 1, 6, whatever comes next, and those would be the coefficients, the same things as the combinations. Okay, so you do have some methods. Okay, Pascal's triangle on this one, because it's being raised to the 6th, you'd end up with 7 terms. And so when you're thinking about that, you're still doing quite a bit of work, right, for Pascal's or binomial theorem to evaluate each separate term there. So I'm going to show De Moivre's theorem, and actually De Moivre's works out pretty nicely if we use the trig form of the complex number. So probably our main issue right here is if we're looking at De Moivre's theorem, z to the n equals r to the n kis n theta. Do we know any of those things? R and theta? No. Oh, we know n, right? Good. I agree with that. N is equal to 6. Can we find r and theta? Yeah, it's the same work that you did in your warm-up for today. So think back to the warm-up. If you're given something in its rectangular form, how would you find r and theta, the trig values? Okay, so do a little bit of work right now to find r and theta. And here you're looking at just the complex number -1 plus I. At this moment, you could be ignoring the power of 6. Bruin told us in the warm-up to get the modulus r, we should do sort of like the absolute value, the square root of a squared plus b squared. So we would do -1 squared plus 1 squared. And so our radius is the square root of 2. For theta, I can't remember who gave me theta in the warm-up. Oh, Hannah gave us theta in the warm-up, the argument. She said do the inverse tangent of b over a. So we do the inverse tangent of 1 over -1. We talked about one like this yesterday where if it's the inverse tangent of -1, you know that from the unit circle. So you could either use your unit circle knowledge or type it into your calculator. If you type it into your calculator and you're in degree mode, it'll give you -45 degrees. But remember that little statement, we always want this theta to be between 0 and 360. So now we backtrack up to our complex number, -1 plus I. Think about what quadrant we would graph that complex number in. Left 1, up 1. That would be in quadrant 2. So my theta is really 180 minus 45, or 135. So now Nick gave us n. We have r. We have theta. We're ready to plug into De Moivre's theorem. And we will get something like this. Z to the 6th equals the square root of 2 to the 6th, kis, n, which is 6, times theta, which is 135. Is everybody okay with my substitutions into De Moivre's? I would kind of clean that up a little bit. Square root of 2 to the 6th you can do in your calculator, but I could also do that in my head. A pair of square roots of 2, square root of 2 times square root of 2 will equal 2. And there, because I have 6 of them, there will be 3 pairs, so 2 times 2 times 2 will be 8. And then this, I think, comes out to be 810. Okay. Now, this one, I'm not so concerned that it's between 0 and 360. It's the very first argument that you would ever find that you need to watch out for, that it be between 0 and 360. If I said that you could leave your answer in trig form for De Moivre, you'd be done. Okay, you have trig form, r kis theta. This is your answer in trig form. What would you do if I asked for it in rectangular form? You gotta find the A and the B. Okay. Now, essentially what you're doing to get the A and the B is working out this KISS, the cosine of 810 and the sine of 810. So you could go to your calculator at this point and do 8 times the cosine of 810. What does that give you in your calculator? 0. Okay, think about this. If you were to find a coterminal angle to 810, subtract 360 twice, that's subtracting 720. Coterminal angle to 810 is 90 degrees. So the cosine of 90 would be 0, 8 times 0. The sine of 90 would be 1. And if you type 8 times the sine of 810 in your calculator, it'll give you 8 times 1 or 8. So 0 plus 8i, which is really just 8i. Okay, so this is my rectangular form. If it didn't match up to an angle on the unit circle, the coterminal angle, you could give a decimal value. Okay, I'm okay with that if you're just typing those into your calculator. 8 times cosine 810, 8 times sine 810. We okay with that switch to rectangular? Okay. Any questions? All right, I want to give you one that you try on your own. Could you please raise to the 4th the complex number 3 cosine 60 plus I sine 60? If you are a fan of our abbreviation KISS, you are more than welcome to write that in that form. So you just have to write less. Using De Moivre's theorem. And I'm going to ask you this. Find the answers in trig form, and then also convert those answers to rectangular form. So if you could get me both forms. Good, I saw Blake wrote it in KISS form, 3 KISS 60. So if you want to change that to 3 KISS 60 to the 4, that's the same thing. What's kind of nice about this one compared to our last example? It's what? Okay, there you could use numbers from the unit circle. Good. Anything else really nice about this one? It's already in the trig form. So on the last one, -1 plus I, we have find r and theta. Here, they're just kind of staring at you in the face. N equals 4, r equals 3, theta equals 60. Remember, n is the power that you're raising the complex number to. Using De Moivre's, we're going to say z to the 4th is r to the n, 3 to the 4th, KISS, n times theta, that would be 4 times 60. So z to the 4th equals, I saw this as I walked around the room, 81 KISS 240. That would be your trig form answer. And then if you wanted to go the step further, which is good practice, and just pay attention to the directions, what form should you be leaving your answer in? If you want the rectangular form, you have two options here. So we've got 81 times the cosine of 240 plus I times the sine of 240. And like David said, those are values on the unit circle. So if you want an exact number, you could use the unit circle. The cosine of 240 is really negative 1/2. The sine of 240 is negative square root 3 over 2. So I could do 81 times negative 1/2 and 81 times negative square root 3 over 2. And maybe if I'm writing an exact answer, I get something like negative 81 over 2 minus 81 square root 3 over 2i. Okay, that could be an exact answer. I would also be okay on this problem if you did that in your calculator, the cosine and the sine. So on this one, I'm a little less picky with the exact answer. If you do 8 times cosine 240, and that should give you negative 40.5, and then you do 81 times sine of 240. Does that give you 70.15? Am I right? Okay. Minus 70.15i. I'll accept either of those answers. Those are both fine with me. Any questions? Okay, now we have tackled the first part of today, which is doing the powers, okay, and that is with de Moivre's. You are responsible for de Moivre's theorem, so you need to know that for your test next Tuesday. I would think back to like that work that we did at the very beginning where you actually found the pattern on your own, okay, r to the n, kiss, and theta, okay. And then here's roots of complex numbers, and this will be provided to you on the test. Finding nth roots of complex numbers for a positive integer n. The complex number z equals r kiss theta has exactly n distinct nth roots. And I'll talk about what that means, n distinct nth roots, given by this formula. Now, it looks a lot worse than it really is, but remember, this is not one that you have to memorize. It will be provided to you on the test. Okay, so that will be helpful in that respect. And I've got some other statements down here. Now, I'll also say it probably looks worse than it is. This is how you'd see it in a textbook, and how it's represented on the test. In your notebook, if you wanted to, and you're comfortable with KISS notation, you can make it look a lot nicer by writing it with KISS instead of the two separate ones. So I'll write it as KISS down here. That doesn't look terrible. No, it's not so bad. You'll end up loving it, trust me. I didn't really mean that. I'm guessing you might not. Now, the good news is tomorrow in class we'll have time. We're going to have a day like where at the beginning we review 6-5. So I have a review activity for you from both days of 6-5. And then you'll get your test review, and Monday is test review, and then the test is Tuesday. So you get 2 days just to let everything settle in your brain. Okay, so we have a couple of things to talk about before we get into an example with this. First of all, we're not finding powers of a complex number, we're now finding the roots of a complex number. So think about just mathematically when you find roots of things, like I'm finding the cube root of 8. I'm finding the number that multiplies by itself 3 times to give me the number 8. And when you do some roots, like 4th roots of 16, there may be algebraically could be 2 solutions, 2 and negative 2 would multiply by itself 4 times to give you 16. Okay. So there's a statement here that when we are taking an nth root, we'll have exactly n distinct nth roots. What that means is distinct is different roots. Okay? So that qualifier is down here with k. So there's a new value in this formula, and that's the k with the plus 2 pi. So think about like all the times we've added and subtracted 2 pi, we're finding like coterminal angles. Okay? And so if we multiply that by k, we're just doing another revolution and another revolution. You only need to go from k equals 0 all the way to n minus 1. So that's going to change depending on what n is. If you're doing a square root, you would do 0 and 1. If you're doing a fifth root, you would have k's 0, 1, 2, 3, 4. And so the more roots, or the higher root that you're taking, the more distinct roots that you have. You have more roots, it's just that they repeat themselves. So then they start to revisit the same roots. And I'm going to show that to you visually after our first example so you can see what I'm talking about. But yeah, this means that you're going to have to do this formula multiple times. Okay, so let's look at an example. We're going to find the cube roots of 8 kiss 2 pi over 3. 8 kiss 2 pi over 3. Find the cube roots of 8 kiss 2 pi over 3. What you know?
We have to find it k is 0.
We will do k as 0. Nope, you'll always start at 0. And why did you say just 1 and 2? Okay, good. So David's already on a roll. He's excited about this one. I like it.
Don't
Nobody will be mad at you, David, for showing a little excitement.
I'm mad at
It
you.
helps build the excitement in the room.
You know what?
We're all excited.
Okay.
Okay, so we want to find the cube roots, which look out for that. Like that's n, right? That's giving you the value of n. So, but it's listed as a word instead of a number. So we see cube and we know that n is equal to 3, which means the values of k for which we're going to do this formula would be k equals 0, k equals 1, and k equals 2. That's my n minus 1. 3 minus 1 is equal to 2. Okay. And I'm going to just kind of do my formula. What do I have? The nth root of r kiss theta plus 2 pi k divided by n. So we now know k's 0, 1, 2. What else do we need for that formula besides k? We need r and theta. Do you know r and theta? Yeah, r is equal to 8, theta is equal to 2 pi over 3, and we also know n already is 3. So then I'd say we're ready to plug in. You can do it how you like, but I'm the kind of person that I'm going to set up all 3 of them first before I do any calculating and simplifying. So I'm going to say z sub 0 equals the nth root of r, so the cube root of 8, times kiss theta, 2 pi over 3, plus 2 pi times k, which in this example is 0, and then divide by n, which is 3. And then I'm going to go through and I'm going to do z sub 1 and z sub 2, because now the only thing that will change in that formula is k. So that 0 is going to turn into a 1, and then 0 is going to turn into a 2. So I'm going to just copy what I see. Cube root of 8, kiss 2 pi over 3 plus 2 pi 1 divided by 3 equals cube root of 8, kiss Okay, so that's kind of like a me thing. I want to write down all the formulas first and then go back and do my cleaning up. Okay, you decide which order you like to do it. You like to just complete one root and then move on, or set it up kind of like I did. Okay, well, what's really nice is some of this stuff is the same. That piece out in front, cube root of 8, 2, right? Okay. So I know that each time I do that, I'm going to get 2 for the cube root of 8. The rest of your work is in this piece with the theta plus 2 pi k over 2. And these, I think, this is an example of what I feel is the worst case scenario. It's in radians, so I got that fraction, 2 pi over 3. I'm going to have to add the 2 pi and then still divide by something. So to me, that's the worst case scenario. Okay. So I'm going to just work it. 2 pi over 3 plus 2 pi 0. Oh, that one's not so bad. 2 pi times 0 is just 0. And so I really have 2 pi over 3 divided by 3. What is that equal to? 2 pi over 9. So think about this. 2 pi over 3 divided by 3 is like dividing by 3 over 1. So that's 2 pi over 3 times 1/3. So that 3 that n that you're dividing by is belonging in the denominator. Okay, so it gets multiplied by the 3. So it should be KISS 2 pi over 9. Okay, z sub 1. Well, I know I'm going to have that 2 out in front. And then I've got KISS 2 pi over 3 plus 2 pi times 1, which is really just 2 pi. And that's like 2 pi over 1. I'd like it to have the same denominator so I could add it together. So 2 pi over 1 is really 6 pi over 3, isn't it? Okay. And then I'll be able to say 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. And 8 pi over 3 divided by 3 is 8 pi over 9. So you start to notice there then some patterns that will be helpful. If you do the little bit of extra thinking on that first one, then you'll know your denominators could come out tonight. And I got one more to do. This time I'm doing 2 pi over 3 plus 2 pi times 2. That would be 4 pi. And that would be 4 pi over 1. I'd like it to have a common denominator of 2, so I'm going to call that 12 pi over 3. That's the same thing as 4 pi. Okay. And then add 12 pi over 3 plus 2 pi over 3 is 14 pi over 3. 14 pi over 3 divided by 3 is 2 KISS 14 pi over 9. So you're doing a little bit of work there, simplifying those angles. Okay, it's not necessarily the nicest thing, but you kind of get in a mode and they all can work the same way. And like I said, I think that's the worst case scenario right there. Okay, all of these answers are in what form? Trig form. Can you put them in rectangular form? Yes. And I'm going to do that so that we can see visually what these things look like. Here's what I'll say. If you're putting them into rectangular form, use a calculator. I'm not expecting you at this point to do any work on the unit circle or find an exact answer. So what I would do is I'd pull out my calculator and I would do 2 cosine 2 pi over 9. Type that in. What mode should my calculator be in when I do that? Radian mode. Okay, so here I have an angle in radians, so I should be in radian mode. Okay. So I do 2 cosine 2 pi over 9. I have mine written down. I get 1.53. Yep, 1.53. And then I got to do 2 times sine of 2 pi over 9. Which I get 1.29. Thanks. And then I would do that for the next two angles. To cosine 8 pi over 9 to sine 8 pi over 9. So this is just a matter of plugging that into your calculator. And I would maybe jot these things down so you have them in your notebook. And if you don't get to try them in your calculator, maybe make yourself a note like try these in your calculator. Make sure you can get these numbers. Are there any questions about how I'm getting those decimals? Are we comfortable with what I'm doing in my calculator even though I'm not showing it to you? Here's what I want to do with the rectangular form. Our modulus for this problem, our R value was what? 2. So it's talking about a circle with a radius of 2. I'm going to draw a circle, radius 2. And you just found the roots of a complex number. Okay? And if I plot them, so I'm going to plot these 3 in rectangular form. My first one is 1.53 plus 1.29i. So I'm thinking about the complex plane. 1.53, 1.29. Okay, so there's z sub 0. Negative 1.88 plus 6.8. There's z sub 1. And 0.35, negative 1.97. There's z sub 3. Look at this visually. Do you see how those 3 roots are breaking up the circle into 3 equal parts? Okay. And so this is z sub 0, z sub 1, z sub 2, I should say. 3, don't know why. Z sub 2. If I were to do z sub 3, it would just land right back here. They're going to be evenly spaced. So it goes in a cycle. Z sub 3, Z sub 4, Z sub 5, Z sub 6, Z sub 7, Z sub 8. So that's what it means when it says 3 distinct roots. Those are the distinct ones. If you keep going, you're just going to get the same numbers over and over again.
So I'm going to be 4 with the circle.
It's split it up into 4 equal parts. Yep. Now, there might be some examples in your homework, so just really quickly, like this where it says find the 5th roots of 1. This is in rectangular form. 1 plus 0i. You know the 5th root of 1 is 1, so that should be one of your answers, but there are 5 distinct roots in the complex set, so some of them are imaginary, okay, and you need to find them. The other thing that you can do on a problem like this is if you'd rather work in degrees, then you can adjust to do like the nth root of r, KS, and do theta plus 360k divided by n. So if you want to give your answer, switch back into degree mode. If your angle is given in degrees or you're allowed to find your angle, you can choose to work with 360 instead of 2 pi. But if you're working with 2 pi, you need your angle to be in radians. Does that make sense? Okay. You have homework assignment. Do your best to try some of those problems. At the beginning of class tomorrow, we'll go over those answers and questions that you may have. Then you'll do an activity to practice all the stuff from 6.5, and you'll be receiving your test review. So chapter 6 test. When is your chapter 6 test? Tuesday next week. Excellent. Yeah. Will you come up here? Chase me.
Can you show me how to put it?